Today we're going to talk about motion in one dimension. Kinematics. Kinematics is part of mechanics that studies motion without its cause. So in this chapter we are going to talk more or less about kinematics, which is, as we said it, like the study of motion without its cause. Another branch of mechanics that studies motion with its cause is known as dynamics. But today's class is more about kinematics. So what are the different physical quantities that we need to quantify motion? To quantify motion, the following three concepts will be discussed: displacement, velocity, and acceleration. What is displacement? Displacement is defined as the change in position. That means what is the distance, the straight line distance between 2 points. That's the shortest definition of displacement. Displacement only talks about like the change in position. By how much did the position change? That means we're only concerned about like the straight line distance between 2 points. It doesn't matter like how you traveled that or traversed that path. What matters is like where you started and where you ended up. As a result, displacement is equivalent to delta x equals x final minus x initial. Keep in mind, displacement is not distance. Distance is like the total path taken by an object, whereas displacement is delta x. For instance, if the motion is along the x direction, that means where it starts and where it ends up. As an example, if I throw a ball straight up and then catch it at the same level, then its displacement is going to be 0, whereas its distance is going to be twice the height it climbed. So now in this chapter, would like to revise vector and scalar quantities. Vector quantities are quantities that are expressed both in magnitude and direction. That means direction is important in a vector quantity, whereas in a scalar quantity, you can completely describe the object's motion in terms of magnitude only. So a good example of a vector quantity is displacement. Displacement is a vector quantity, whereas distance is a scalar quantity. Now, one of the physical parameters or quantities that we would like to discuss when we describe motion is speed. Speed is defined as the total distance traveled divided by the total time elapsed. As a result, like mathematically speaking, V equals d over t, where d represents the total distance, t represents total time. Speed is a scalar quantity, like distance. The SI unit of speed is meter per second, whereas velocity is defined as the rate of change in displacement. In other words, displacement divided by time gives you velocity. As we defined it earlier, displacement is equivalent to final destination minus the initial destination. That means what it cares is just the straight line that connects the initial and the final location of the object. So the average velocity, as we said it, like we already defined it, is the rate at which displacement occurs. It is a vector quantity, and at the same time, it can be positive, it can be negative. A positive velocity means the object is moving either in the positive x direction or along the positive y direction. Negative velocity means the object is moving in the negative x direction or in the negative y direction. Okay? So the SI unit of velocity is meter per second, like the SI unit of speed. Now those two blue and red color diagrams depict a very good example, the difference between speed and velocity. Let's consider there are two cars. One is a blue car and the other one is a red car. The blue car takes the blue path, whereas the red car takes the red path. Both of them started at point x initial, at point P, and both of them ended at point Q. Both of them started at the same point, and they finished the race at the same time at point Q. So what do you learn from here? What we learn from here is like the total displacement for the blue car and the total displacement for the red car are the same. That means their velocity will be the same. Whereas the total distance traveled by the blue car is longer than the total distance traveled by the red car. As a result, the blue car has a larger speed compared with the red car. The other parameter I would like to discuss in this topic is acceleration. Acceleration is the rate of change of velocity. That means how the change in velocity is occurring per unit time. In other words, mathematically speaking, acceleration is equivalent to the change in velocity divided by change in time. Like velocity, acceleration is a vector quantity. It can be positive, it can be negative. The SI unit of acceleration is meters per second squared. Meter per second squared. Keep that in mind. So acceleration is the rate of change in velocity. If an object is speeding up, then it has acceleration. If an object is slowing down, it has acceleration. If an object is just moving at a constant velocity without changing its velocity, then its acceleration is 0. Then let's go ahead and then try to solve some examples. Motion diagrams. In a motion diagram, if someone gives you like a set of displacement data with time, then from that, by graphing the displacement versus time graph, you can determine the average velocity between 2 points. Likewise, if someone gives you a set of velocity data with time, then you can plot the velocity versus time chart and you can determine the average acceleration of the motion. So how do we determine those things? So the average velocity is equivalent to the slope of the line that joins the initial and final positions on the graph. Likewise, the average acceleration of the object can be determined by finding the slope that joins the initial and the final velocities. What is a slope? Slope is equivalent to the change in vertical axis divided by the change in horizontal axis. Sometimes it's defined as rise over run. Rise means the change in the y-axis, whereas the run represents the change in the x-axis. Just to summarize our motion or our motion diagram, if you look at A, row A represents a car moving at a very constant velocity. In that case, its acceleration is 0. If you look at B, the car, as every time passes, the car is moving further and further every second. That indicates that its acceleration is increasing. Both the velocity and the acceleration are in the same direction. Whereas in diagram C, if you look at it, the velocity of the car is decreasing as time goes by. The size of the arrow indicates how far or how fast the car is traveling. A smaller or shorter red arrow means a slower velocity. As a result, in diagram C, the acceleration of the car is in the opposite direction. Sometimes they define it as a deceleration or slowing down. Then, in this particular case, you may say the acceleration is opposite to the velocity, its direction. And then probably let's have some examples. One-dimensional with motion with constant acceleration. If acceleration is involved in a motion, right? So as a result, you can do some calculations that involves different given parameters using the following equations. Those equations are known as kinematic equations. So keep in mind, the kinematic equations are applicable if you have uniform acceleration. V, first equation, represents V, which is the final velocity of an object, is equivalent to the original or the initial velocity of the vehicle or the object, plus acceleration times time. The second equation represents delta x, which is the motion along the x-axis, is equivalent to the average velocity multiplied by time. The average velocity means the initial velocity plus the final velocity divided by 2 multiplied by time. The third equation represents delta x is equivalent to the initial velocity multiplied by time plus half times acceleration times t squared. And the last equation represents the final velocity squared is equivalent to the initial velocity squared plus 2 times acceleration times the change in displacement, the change in displacement. So when do we use those two equations or those four equations? So the notes are the following. You will be using this equation if you know the initial velocity, the final velocity, and the time. Okay? So then the other equations, depending on the given circumstances, you are allowed to choose what equation to use. Let's go ahead and solve some more examples. Free fall. Free fall originally formulated, most of the concepts of free fall are originally formulated by Italian scientist Galileo Galilei. Then a free fall is a uniformly accelerated motion, only that it's in the y direction. That means in the vertical direction. Then always the gravitational acceleration in this class will be considered as negative 9.8 meters per second squared. Why? Because no matter what, whether the object is moving in the upward direction, if throw a coin up in the air, it slows down. That is because the gravitational acceleration is towards the Earth's gravity. If you throw a coin downwards, right, then the coin will accelerate. That means its speed will keep on increasing because it's accelerating towards the center of the Earth. In all the circumstances, the acceleration is always towards the center of the Earth. So if y-axis up is positive, then gravitational acceleration is always negative because it's always towards the center of the Earth. All the kinematic equations that we saw in the previous slides, they are applicable here for free fall, because free fall is a uniformly accelerated motion. There are varieties of free fall. One is an object dropped. If you drop an object, what happens? Its initial velocity is considered as 0. When you read the problem, if it states that like object is dropped, then its initial velocity is 0, whereas its acceleration remains negative 9.8 meters per second squared. What if an object is thrown down? If an object is thrown down, that means what you need to consider is its initial velocity is negative, because its initial velocity is in the negative y direction, whereas still acceleration has to be kept at negative 9.8 meters per second squared. What if you throw an object in the upward direction? In that case, what you will consider is its initial velocity is positive, and its velocity at the top of the height, or once the ball or the coin climbed up, and then it will instantly stop, and then it will start to come back. Then its velocity right at that spot is equivalent to 0. Whereas its acceleration throughout the trip is negative 9.8 meters per second squared. So if you throw an object in the upward direction, right, the motion may be symmetrical. That means if it goes up and then comes back down to your hand, if you throw a coin up and then if it comes back to where it started, then the motion is symmetrical. That means its time to climb up is equivalent to the time to come down. And the final velocity at which the ball comes back is equivalent to the initial velocity when you throw the object in the upward direction. Sometimes, what if the motion is not symmetrical? If the motion is not symmetrical, then you will have to break up the motion into various parts. Sometimes the upward direction motion, and then you break it down, and then you solve some parameters for the downward as well. Let's go ahead and then try to solve some examples. Thank you.